All right, welcome back. So we're going to do basically the same problem, but it's going to be a three-dimensional version. Okay, it's the one we did in the last video. So we're going to optimize, or we're going to maximize, okay, f of x, y, z equals x times y times z. And our constraint is going to be g of x, y, z equals x plus y plus z equals L. Okay, so we're going to look at this both directly and with Lagrange multipliers. Okay, you can probably guess I really am a fan of the Lagrange multiplier method, and we'll see. I'm going to, never mind. Okay, directly. Okay, so directly we're going to reduce the dimension of the problem. We're going to say, okay, we're going to, let's say z equals L minus x minus y, and we're going to take f of x, y, L minus x minus y equals x times y times L minus x minus y. Okay, let me rewrite that as xyl minus x squared y minus xy squared. Let's take and find the critical points there. Gradient of f equals, first the derivative with respect to x. So we're going to get yl minus 2xy. Next, the derivative with respect to y. And that is xl minus, oh, I forgot a term, minus y squared there. xl minus derivative of this with respect to y is x squared minus 2yx. Okay, critical points. Remember, critical points happen when the derivative is equal to 0. So we need both of these to be equal to 0. So let's write those. Let's factor out a y. L minus 2x minus y. Yes, okay. So this gives us y equals 0, or y equals L minus 2x. Okay. Next, let's look at the other one. xl minus x squared minus 2yx. Factoring out an x. L minus x minus 2y. Okay, so x equals 0, or x equals L minus 2y. Okay, so now 0, 0 is a critical point. Okay, but what happens if x and y are both 0, or either 0? Then we're going to get 0 here for f of for our f. Okay, so that's not going to give us our maximum. We want a max, right? Okay, so let's take a look at these points. X equals L minus 2y and y equals L minus 2x. That's basically, those are two lines, right? So let's take a look. So if x equals L minus 2y and y equals L minus 2x, okay, then I'm going to go ahead, I'm going to write that as L equals x plus 2y, L equals y plus 2x, and those should be equal. So okay, so doing a little bit of algebra magic, we're going to get y equals x. Okay. If y equals x, let's go back. Z is going to be L minus 2x. Or rather, x plus y plus z equals L. Ah, okay. Now, one more thing. L equals x plus 2y. Okay, so that means that, yes, that means that 3x equals L, so x equals L over 3. So all of these things are L over 3. Okay, so we found a point. Now you plug that in, that's going to be a max. You take the second derivative of this thing. So let's call it f. And you can take the second derivative matrix to find that you're going to have a max there. Okay. I really don't do that with these unless I have to. Generally, I'm just going to do the whole game of let's find our critical points, plug it in, and then we just list them off. The highest one is the max, the lowest one is the min. Okay? Let's revisit this problem with Lagrange multipliers. There we go. So let's optimize or maximize f of xyz equals x times y times z with our constraint g of xyz equals x plus y plus z, which we set equal to L. Okay? It's going to follow the same sort of pattern with a twist. Okay, so let's take our gradient of f equals lambda gradient of g. Okay, so the gradient of f is going to be the derivative of this with respect to x is y times z. Let's actually do it in, and that should equal lambda, right? Derivative of this with respect to x is 1. Then x times z also equals lambda. Sorry. And then x times y also equals lambda. It's interesting. All right, so now one of the things I do here is then I multiply these in order to get the same thing. So what I'm going to do is I'm going to multiply this equation by x, this equation by y, and this equation by z. And what does that mean? Well, I'm getting again to my x equals y equals z solutions. Oh, that's really nice. Once I have x equals y equals z, then I have, they're all equal to L over 3. Okay, and that's going to be a max. Okay. All right. Next video, I'm going to show you what to do if you don't have this nice symmetry. Okay?